Hello, Bloomfield High, and welcome. Today we're going to get started on some radicals and being able to try to simplify and looking at the difference between what is a square root radical and a cube root radical and how those variations work as far as being able to simplify the radical. So here we go. First problem that we're looking at here, problem number 1, we want to be able to figure out how do I simplify this radical down. Well, the first part I can notice I have a 7 that's going to be multiplied by that, and what I usually think about that as being is this 7 is now kind of off to the side. I know I'm going to multiply 7 times whatever this radical simplifies down to. So I just kind of ignore that and set that off to the side. Now, for square roots, we can think about this as being an imaginary 2 out front. And what you've thought about in the past is where I can say, well, what is the biggest perfect square that may be factors of 96? So I can think about factors of 96 being 16 and 6, where 16 is a perfect square. Right? And so I could say, well, for the number part of this, I could say that this would be 4 square root of 6. Right? So that's one way of doing it. For the m, I usually think about this as being 3 m's, right? M cubed. And since it's square root, they have to come out as a pair. So one pair of m's, or m squared, comes out and picks up the extra m here. So I end up having 7 times 4m, right? 7 times 4 times m, square root of 6. Or the answer here, 28m, square root of 6. So that'd be the answer for number 1. So another way to kind of approach this problem as well, I can once again think about the 7 as being kind of set out to the side. And I can break in this 96 into just simple multiples. So 2 times 48, and then I can take, all right, well, 48 is 2 times 24, and 24 is 4 times 6, and this is 2 times 2, and I'm just going to go with that. Well, then, because it's a square root, once again, I have a pair. So there's a pair of 2's. There's another pair of 2's. So I have 2 pair of 2's, which would come out as a 4. So I have 7 times 4, right? And then once again the m's, I have 3 m's, and they come out as a pair. So one pair, so it gives me an extra m, and I can see that I also get 28m square root of 6. I personally like this way much better because it works for multiple different sets of problems, not just square roots. Now, one approach I would have when I have these really large numbers, I want to kind of figure out maybe what is a large number that I could possibly divide this by. Well, one thing that I tried, I'm just going to say, well, that breaks down. I just did 384 divided by 16 and just see if it worked. And this gives me 16 times 24. Well, these I can break down real fast. I know that this is 4 and 4. I know that this is 4 and 6. Right? And then I can take my x's, and I got 4 x's. And I got 3 y's. And since it's square root, there's a pair. Here I have 2 pair, right? So I know that's coming out as 2. I can say, well, I got, here's a pair of 4's. So those can come out as a 4. And this can break down to 2 times 2. And this can break down to 2 times 3. So I can get a pair of 2's. So what is left? I got 4 and 4. So I got a 4 times a 2. And I have inside the remainder square root 6. And for x's, I get 2 x's that come out, or x squared, and I get a y that comes out. So my answer is 8x squared y, square root of 6y. And there we go. Look how easy and how quick that is. Now, well, when you're trying to attack cube roots, there's a couple of different ways you do it. You can think about maybe trying to find what are some perfect cubes. So like 2 cubed is 8, 3 cubed 27, 4 cubed is 64, 5 cubed is 125. And really you don't need to go any higher than that, but you really do need to know all of those pretty much right off the top of your head. So I could say, well, this can be broken down. I know 54 is the same thing as 27 times 2. And if I do the cube root of those, I end up cube root of 27 is simply 3. So this gives me 3 cube root of 2. So that one's pretty quick and efficient to be able to do that way. And I can break that down, that process. If you didn't see it that way and don't see the perfect cube side of things, once again, you can do it the other technique and you get the same answer. So if I wanted to be able to do, all right, well, I see that, I know it's 9 times 6, I know this is 3 times 3, and I know this is 3 times 2. There's 3 3's, so 3 3's come out as 1 3, 3 square root of 2, and I'm done. So whichever way you see is a little bit faster. Personally, I think this way may be a little quicker, unless you can see, that 54 is definitely 27 times 2 really fast and efficiently. For number 4 here, what I would be able to do is, once again, I think about that -2, and I'm just going to kind of pretend like that doesn't exist for a second. I'm going to deal with the number first. Well, what I usually do for these kind of larger numbers, I just see, well, maybe what can go into there, and I try and just see, well, 16, this is 16 times 12. And so I can break that down into 4 and 4, and this as 4 and 3. And so there's my 3 4s. So 192 is the same thing as 4 square root of 3, cube root. For the letters, I have a squared. Well, they can't, I can't pull any of those out, so those have to stay because they're not groups of 3. The B6, just simply divide that out, and so I can pull out, right, 2, because I got 1, 2, 3, 4, 5, 6. There's 2 groups of 3, so it comes out as b squared. Now I have a -2 times the 4, so I get -8 b squared cube root of 3a squared. And there's our final answer. Pretty easy.